Okay, today we're going to topic 5, and we're going to go to topic 5.1, which is on electric field. I'm going to start off with some fundamentals, and which you have probably seen before. I just like to challenge your understanding of those fundamentals. Then we build on those fundamentals, and we have done gravitation before. I go draw parallels between whatever I'm going to do with gravitation, which you're familiar with, and then I'm going to show you what is different between electric field and gravitation. So we start off with familiar grounds, and then we go off to the unfamiliar grounds. Okay? So let's start off with something that you have seen before. If I ask you to draw the field pattern of electric charge, a positive electric charge, how will it look like? It will, okay, can. So there are two things that I'll look out for, outwards and radially from in all direction. There are a couple of things over here. If you didn't realize, there are a couple of things. First question, why is it pointing out? Who says so? Who says that it must, yeah, exactly, someone says so. Why is it a negative charge must point in? Who says so? Second point. Can you see that these are all perpendicular to the surface? Who says so? Why cannot draw like this? Why cannot draw like this?
It doesn't look
or like this? Why cannot? you never why like why not like this? Yeah? Why is it that every textbook you see, it will always be perpendicular? And third point, because as a consequence of the second point, why is it that they all point towards here? A need, right? That's not a very scientific reason. It's need, what? Therefore, it's easy, what? Come on. But that's it. Everything in this world happens in a way where it is in harmony, where it is elegantly designed. That's it. You're correct. Yeah, scientific elegance. Something, probably arrange it so that it is elegant. But that's it. Elegant from our perspective. Yeah, elegant from our define of the world. Now, let's deal with this problem one by one. Let's start off with the issue of why is it that the field lines point outwards. Okay, I'm going to give you the definition of electric field, and you'll understand why is it that all the electric field pattern that you draw is always pointing out from a positive charge, pointing into a negative charge. Now, electric field is defined, or electric field strength is defined as the force per unit positive test charge at a point. Can you tell me which part of this definition is the one that tells you that the electric field pattern due to a positive charge must be pointing out? Which part of this definition tells you that? Exactly. So what we define electric field is, if we got a positive charge, how do I know how strong the influence of this positive charge is at this point? How do you know that? So what we do is, we put a small positive charge, small test charge, and the force on this small positive test charge, we define it as the strength. Yeah? Per unit charge, that means on 1 coulomb of the charge on a small charge, the direction and the magnitude of the force will be the defining quantity that tells us how strong the field is. So you understand why is it that for positive charge, the field always points outwards, because the force on the positive test charge is this way. And if I were to have a negative charge, if I were to place a positive charge based on definition, the force will be this way. And that's why the field due to a negative charge points inwards. Now this is the language of physics, which means that if I give you some weird pattern, like this, how do you know what's the direction of the force on the charge? Positive charge, the field lines goes like this, so you draw a, not gradient, the word that starts with T, tangent, exactly, tangent, so the force goes this way. Question number 2, for you to think about, is it correct to say that the particle will follow this?
Yes.
Hang on, before you answer, I was just about to say before you answer. Before you answer this, think about this. I got gravitational field this way, right? I project a particle this way. This is gravitational field. Are you telling me that the particle will go this way?
No. It's too light.
So why do you say that the particle will follow this way?
That just depends on the result factor.
Yeah, so it depends. You see, I'm saying this because from my experience in teaching, most students will say that the particle will follow like this. It won't. You just need to draw parallel to this. The particles will not go this. They will go closer and closer, right? So it will not follow. But the initial force is definitely this way. Because why? By definition. Okay? Cool. So the usual cognitive fallacy that students will fall into is that when one is 0, the other one also 0. When velocity is 0, acceleration is 0, displacement is 0. Not necessarily true. When acceleration is 0, velocity is 0, displacement is 0. Not true. So be very careful about all these things. Yeah, before you make conclusions, before you make jumps, be very careful about this. Cool. So let's go back to the simple things that we are talking about. Now we talk about direction. Electric field obviously is a vector quantity. And why is it obvious? What part of this definition tells you that it's a vector quantity? There's one word that tells you that electric field strength, exactly, force. The force. It's a force per unit charge. So it is a vector quantity. So electric field strength over here is a vector quantity. Now vector quantity has both direction and magnitude acceleration. So we have talked about the direction. Now we're going to talk about magnitude. So the equation for electric field strength is E equals to KQ upon R square. If you have friends in A levels, if you get notes from them, they will show you the notes showing that this K over here is 1 upon 4 pi epsilon naught Q upon R square. The thing is that this has an unfriendly number value of this, whereas this has a very friendly value of this. So personally, I totally prefer the first one. In fact, if you use 9 times 10 to the power 9, it's 1% off only, so it's still okay. Can? So you have a better deal of using this equation. This is in the IB syllabus, so the first one. Can? But those of you who are in Olympiad syllabus with me, you'll find that this is actually, it gives you a reason, it gives you an understanding of why it is so. Just that we group this and call it K. Can? Cool. Now, let's just plug in numbers and get a feel. So, you've got a positive charge over here. Can you find the Q so that this is 0.5 meters, this is 1.5 meters? Can you find the charge so that the E at X is equals to 1 Newton per Coulomb? Simple question. Can you find the charge over here so that the field over there is 1 Newton per Coulomb? I'm waiting for a question. You know K. You know E. Do you substitute 0.5, 1.5 or 2 into R? Yes, it's 2. As you do the question, the numerical question, think about why. Why is it 2? Why is it 2? Why must it be 2? 2 meters, I mean.
Yeah.
It's the same question as gravitational field. If you got R and then you got R, X, why do you substitute 2R?
So X from the center.
Yeah, it also X in the center, but you need to appreciate from, rather than just mathematical convenience, you need to appreciate that it's actually quite elegant in the sense that you got mass everywhere. You got influence of mass over here on this point, mass over here on this point, mass over here on this point. Somehow it just ends up in a way where the effect is right at the center. Same thing, if you got a conductor over here, the charge is actually distributed all around. We'll talk about why is it distributed all around later. But it is distributed all around in such a way where the collective effect is as though it's at the center. And that's the reason why when we draw the field pattern, it extends outwards from the center because the effect is as though it is at the center. Understand now? Yeah. Okay. So, someone tell me what's the Q? 4.45? 10. Yeah. Small amount of charge. Very, very small amount of charge. How small is this charge? If you have a 1 amp current, which you can easily get connecting a 1.5 volts battery to a 1.5 ohm resistor, a 1 amp battery will take less than 1 nanoseconds to charge up this amount. Really, really small. Yeah. And you experience a 1 Newton force if you have a 1 Coulomb charge here. So actually it's electric force. That's why electric force is a more predominant force as compared to gravitational force. Yeah, it's a stronger force as compared to gravitation. One charge is boring. Let's throw in another charge. Oh, before I go on, anyone had difficulties with this? 4.45? Okay. Let's start off with something that you're more familiar with, which is gravitation. And make a guess, why do I start off with negative charge when I say gravitation? Because the field due to a negative charge points inwards, like a gravitational field. Right? Gravitational field also point inwards. So negative charge also point inwards towards itself. So do you agree that if I've got charge Q over here and 4Q over here, and this is separated by L, there is a point somewhere along here where the resultant field is 0.
Same as gravity.
Yes, exactly. Later I will show you how it can be different. Do you think that it is going to be closer to here or closer to here? Left or right? Yes.
Left.
It's always smaller to here. Closer to the smaller charge. Can you find X upon L so that E resultant is equals to 0? Give it a try. That means the field over here due to the Q is equals to the field over here due to the 4Q.
1 to 16?
No, it is not.
Huh?
It is not. It is not.
I also forgot gravitation.
Yeah, probably use this as a recap for gravitation as well.
I don't have my notes. Is it not?
Yes, it is not. I'm very sure. The answer is so simple that I didn't want to tell you the answer so that in case you re-engineer, I want you to work towards the answer, not work backwards from the answer. Yes, correct. No, it's not. It's 1 over something, if that helps. It's 1 over, then you go down the road like 1 over 4, 1 over 3, 1 over 2, confirm will hit. It's 1 over
17?
a very interesting number. 1 over 17, how do you get that? How do you get that 1 over 17? It's 1 upon 3.
Huh?
1 upon 3.
Root square rather than square. Okay. Never mind. Okay. Square root.
Can? Cool. So simple one now. Now, for those of you who are done with this, the answer is L upon 3. I'd like you to think about what if I were to change this to
But sir, there won't be equilibrium. Why?
think again. I give you 2 minutes to think again. The same question holds. I want you to find the distance from the smaller charge where the field is 0. Ji Yuan's answer is you're correct. Between the two charges, yes. Did I say you must find in between?
It's outside.
It's outside, correct. Then the question is left side or right side? Left side or right side?
Left.
Some say left, some say right. I'll give you 10 seconds to think about. Say left, okay. Okay. So is the left right or the right right?
Left.
Or is the right right, the left wrong? Okay, I'm just trying to confuse you. Remember, the neutral point where the field is 0 is always closer to the smaller charge in magnitude. Yes, correct. It is somewhere here. Now this is the point which is different from gravitational field. Gravitational field, the neutral point will always be in between. Why? Because there's only negative mass, as in like the field can only point into the mass, they will never point out of the mass. At least as far as we understand gravitation to be. There's dark matter, there's antimatter, there's dark matter where they probably think that the mass can actually repel. But in the gravitational field that we understand, it always points inwards, it never points outwards. This is where electric charges differ. So electric charges, there's positive, and that's why the field points outwards. So the field due to the 1Q is equals to the 4Q over here.
It's L.
So I would like you to find X here. Give it a try.
I say it's what? L.
It's L.
Yeah.
Okay.
draw the numerical relationship from last question.
Yeah.
On there.
Yeah.
Sir, is it possible this neutral point is in a curve?
It is there. What do you mean by whether it occurs? It is there.
That makes the story more.
It is there.
What's the shape do?
The shape of the pattern? I mean,
The neutral curve.
oh, there's only one point. So you're talking about the loci of the points where the potential is 0. I think it's going to be more. I'm not sure. I'm simplifying the problem by looking at it only this perspective. Probably it may go this way.
Yeah, it's possible.
I think it goes this way.
Oh, this one?
Yeah, I think.
I don't know, it's 1 to 2, right? Ratio.
Yep, the ratio has to be 1 to 2. Correct. Okay, let's solve this. So using the same thing, E1 equals to E4 KQ upon X squared is equals to K4Q times X divided by X plus L squared. That's the difference. Instead of L minus X, it becomes X plus L. QQ, KQ cancel off, so L plus X upon X equals to 2, and therefore now you got X equals to L. Neat answer. Okay? Yeah. The ratio has to be 1 to 2, the distances, because the charge is 1 to 4. Can? Yeah. But I hope now you start to see the difference between gravitation. There are certain similarities, but there are also certain differences. You need to be honest. You need to understand.
Okay, so
Yes.
So for the Q, that's the absolute value.
The absolute value, yes, correct. Because when we write this, when we write E1 equals to E4, we are inherently saying that E1 minus E4 equals to 0. So we have already taken into account E1 plus negative E4. We have already taken into account the direction, so we don't need to substitute the negative sign in. If you want to substitute the negative sign in, then we should write E1 plus E4 vector sum equals to 0. Then you substitute the negative sign in to show the negative direction. Okay? For forces, I prefer to state the direction first, then just take magnitude for the equation. It's neater that way. When we go to topic 10, when we do energy, we leave our worries then. Okay? So, ready to move from 1D to 2D? We have gone from 1 charge to 2 charges. From 2 charges in 1D, we go to 2 charges in 2D.
Is that 3D?
3D will be the not as big a step up as from 1D to 2D, because 3D is the same as kind of similar to 2D. Okay? Now let's take a look. You have done this in gravitation before, just that there is a additional point about negative charge, a positive charge. KQ, this is negative 4Q, this is 2L, this is 3L.
49. Nice.
This is E resultant. This is charge X. State if X is positive or negative. Find K. Yeah. That's it.
So,
The resultant field at this point is pointing this way. That's all you're given. Hey, hang on, what am I doing? It's impossible.
yeah, minus 49.
Yeah, understand. It's this way. Yeah, it's impossible for it to point down.
So this K is different.
Probably I should use alpha, otherwise it'll be confusing. You're correct. I should use alpha. Otherwise the K and the K will mix up. Okay? Alpha. Negative or positive?
Negative, I guess.
Remember, positive charge, the field points out. Negative charge, the field points in. And if you've got more than one charge creating a field at one point, you have to do the vector sum. That's the concept we are using. So, positive or negative? 50-50. Okay, let's do one by one. The field at this point, due to this charge, is pointing up, right? So looking at the resultant field, where do you think the field due to this charge at this point is pointing? Towards this way, right? So is it negative or positive? The field due to a charge points into the charge. Is it positive or negative? Negative, yes, correct. Yeah. I'm very positive that it's negative. Ha, ha, ha. Okay, Ken, so it is pointing towards that charge. Now, before you do the next part, you need to remember that it is a vector sum. Field is a vector. It's a very modern idea. Field is a vector. Why? Because the definition says that it's a force. But you need positive charge. So, if I were to draw the vector sum, this is E4 plus, I'll write it this way. No. This is E alpha plus E4 gives you E resultant. And this is 60 degrees. And it is a right angle triangle. So the hint to you is to use a little bit of trigo and your knowledge that E is equals to KQ upon R square. Try to find the value of alpha. Give it a try. I'll give you 2-3 minutes to figure out. Use trigo, use E equals to KQ upon R square.
Yeah, it feels like it's 27.
We'll work it out.
Why are you like feeling your way through physics and feel this answer?
So I feel.
That what I feel is wrong.
But the thing is that the difference sometimes between a person who is at that level and the person who is get good results is that feel. I know the answer, but I don't know why I know the answer. You know, that's. Of course, it's better. Then after you know that answer, that I think is the answer, then I work backwards. That's the Einstein kind of, really great scientist kind of level.
Right.
I know the answer, I think this is it, then I try to prove it. Yep. Okay, sorry? Why is it negative charge? You mean this one? Because by deduction, the resultant field is this way. The resultant field is this way. I know for sure that this is this way because it's negative charge. So therefore, to cause a field this way, the field due to this charge over here must be pulling it here. If the field over here were to be here, then the resultant field will point this way. So if it points this way, the field due to this charge at this point must be here. And if any field, remember the first thing I went through is positive charge, the field points away from the charge. To an unknown charge were to point towards itself is definitely a negative charge. Implicitly, I'm using the concept that it is a vector sum. And implicitly, I'm also using the concept that negative charge, the field points towards it. So that's why I started with those two ideas. Very important, fundamental. Okay, let's prove it now. Let's write somewhere closer so they can see. Tangent 60 is equals to E4 upon E alpha, which is K4Q upon 2L square upon K alpha Q upon 3L square. Is it 3L? Okay.